We start now, sir? Okay, so good evening to everyone joining over today, live in YouTube with us. Today we are gonna take up JEE Mains and Advanced series, where we shall be discussing all the recent PYQs, as well as very conceptual questions that will brush up all the important concepts that a particular chapter is having. And I guess if you go through all the solutions with me, then you'll be in a great place in your JEE mains and advanced preparation. I really have picked up great conceptual and difficult questions per se, so that we take time and review the concepts that we have learned and learn to apply them in real life or exam questions. Okay, so let me introduce myself first. Myself, Sashwat Mishra, and I am currently a third year MBBS student at AIMS Raipur. Before this, I was at IITK, where I was in engineering physics department for 1 year, and where I got 9.8% CGPA, but I dropped out from the institute for pursuing MBBS from AIMS Raipur. Okay, so that's all about me. So before we get on, start with the session, I would have a gentle request to all who have joined us live that if you have any doubts around any question, because these are actually very conceptual questions. So I guess people who have joined might have doubts. So if you have any doubts, so after every question, I'll pause and check the comment section. If you guys have any doubts, then we shall clarify for each question then and there, and then proceed over to the next question. Okay. So today we almost have 40 questions, I guess total 38 questions. But I promise you that this session will take your preparation to a next level, and you feel confident after watching this session. Okay, so let's start without much further ado with today's electrostatics one-shot revision for JEE Mains and Advanced. All PYQs and important questions covered. Okay, so here we move on to our very first question. Okay, I guess the question is visible to everyone on the screen first. Okay, so let's begin. Let's read the question statement first. Uh, an insulating long light rod of length L is pivoted at its center O. This is the rod which I am highlighting in red. Okay, this rod is having a length L, which has been mentioned, and it's pivoted at its center point O. Okay, and it is balanced. The rod is balanced with a weight W at a distance X from the left end, as shown in the figure. From the left end, this is the left end of the rod. From the left end, at a distance X, we have a weight W, okay, which is tied down from the rod. Now, charges Q and 2Q are fixed to the ends of the rod. This is the rod, and to the ends of the rod, we fix two charges, Q and 2Q. Okay. Now, exactly below each of these charges, exactly below this charge and this charge, okay, we at a distance h, a positive charge Q, capital Q, is fixed. Okay, here and here, a positive charge, capital Q, is fixed. This distance is h, and this distance is also h. Okay. Then we have been asked what is the value of this X. Okay. Now, uh, when you see this question, actually, this rod is kept balanced by all the forces that are acting upon the rod. Okay. So the basic question or the basic instinct for us should be, first of all, to draw its free body diagram, isn't it? Okay, so let's get on with drawing the free body diagram for the rod first. So here I have the rod, okay? Here I have a charge, okay, which is Q, and here uh, I have another charge, which is 2Q, all right? I put Q here, okay. And this is its center point O, okay, let's assume. Now, here a weight is hanging, okay, W. And just it's a free body diagram. That's why I am drawing the forces here, okay. Weight W acting downwards, okay. At a distance, this whole thing is L, right? This whole thing we have been given as L. And from this here to this W, this length was given to us as X, okay. So from the center, this should be L upon 2. Okay. This should be uh, this whole length is X. This length will be L upon 2. So this one would be X minus L upon 2. All right. So uh, this length is X minus L upon 2. Okay. Now we have two capital Q charges directly kept below these charges, these fixed charges, right? Directly below here and directly below here, we have capital Q. Okay, capital Q and capital Q. So due to this, there will be an electrostatic repulsive force, right? There is this electrostatic repulsive force. Okay, due to this uh, underneath charge. Okay, I'll represent the forces with red color. Okay, so this would be K Q1 Q2 upon this distance was h, right? This distance was h, so it would be h square. This should be 2kq because this charge is 2q, qq upon h square. Okay. So, and this rod itself is not given a weight, it's a light rod. That means you consider it massless. Okay. Now, this whole arrangement, I'll denote this L, not confusion. This whole rod, this whole rod is in equilibrium, right? That means the net translational as well as the rotational force or the net torque as well as the net force on this rod at any point should be zero, isn't it? For simplicity, I'll choose this center point where it is 5 or 10. Okay. And I will find the torque about this point. Okay. Now, the torque is R cross F, right? So this length is L upon 2. And due to this electrostatic force, the torque would be R cross F, right? So it would be, uh, so we will write there is uh, yeah. So there is conservation of moments, right? Conservation of moments about the point O. Okay. So first, I'll write the torque uh, about this force. Okay. It should be from this point. Okay. From this point, all the forces of this side should balance all the forces of this side. The torque of this force should balance the torque of these two forces. Okay. So what should be the torque, the magnitude of the torque of this force? It is K Q1 Q2 upon H square into the distance, right? L upon 2. Isn't it? This into the L upon 2. Okay. Should be equal to the right side of uh, the pivot point. That's equal to, if we take upwards, the force upwards is positive as a torque, then for this case also we take this upwards as a positive and this downwards as negative. Okay, so this equal to 2kq q upon h square into L upon 2, okay, minus W into this W acting at x minus L upon 2, right? To x minus L upon 2. And if you write this equation, if you understand this equation well, we're good to go. I'll explain this equation once again. For this electrostatic force, it is R cross F. The direction of it will be from the right hand, the Cauchy rule, the direction would be into the plane of the paper. Okay, this side. For this force, it's also out of the plane of the paper. Okay, it is out of the plane of paper. And for this W, it is into the plane of paper again, right? So all the into the plane of the papers should balance the out of the plane of the paper, right? So if you rearrange this equation a little bit, this expression you can bring over to this side. So this plus this is into the plane of paper, and this is out of the plane of paper, and these two are balanced. Okay. So now it's just basic algebra. That is W into x minus L upon 2 is K Q upon h square into L upon 2. So x is L upon 2 plus KQQL upon 2W h square. Now, okay, so if you take the LCM now and put the value of K as 1 upon 4 pi epsilon naught, okay, value of K as 1 over 4 pi epsilon naught, you would get it as this equals, this is 4, so it will be 8, right? So 8 pi epsilon naught W h square. But here we have a 2, so this will be 4, right? So it will be 4 pi epsilon naught square, epsilon naught W h square L plus K is 1, so K Q Q L upon 2 W h square. 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 2 W h squ Okay, and multiplied by uh, 4 pi epsilon naught. So this will be 8 pi epsilon naught. Okay, so if you compare in the denominator, it's 8 pi epsilon naught h square w QQL 4 pi epsilon naught. Yeah, so this is the answer to this question. Absolutely correct. Option D. Okay. I guess the concept is pretty simple here. You just had to observe the moments of the torque about the central line. You could have also done the same thing about this point, the extreme left hand or the extreme left hand, and you could have ended up with the same answer. Okay. Doesn't matter because the rod is at rest. Okay. Both rotationally and translationally. Okay. So this question can also be framed as part of rotational mechanics chapter also. Okay, the concept is from the rotational mechanics. Okay, so I guess this question is done and dusted. Great job, guys. First question done and dusted. So let's move on to the second question we have. Okay, all right. So this here is the second question. Let's read out the question first. Okay. A small block of mass m charge plus Q, mass m and charge plus Q, is kept at the top of a smooth inclined plane. This is a smooth inclined plane of angle 30 degrees. Okay, of angle 30 degrees, placed in an elevator, placed in an elevator moving upwards with acceleration a naught. This elevator, this whole assembly is moving upwards with an acceleration a naught. Okay. So it's a non-relativist or it's a non-inertial frame. Okay, it's a non-inertial frame. Okay. Now, electric field E exists between the vertical side walls of the elevator. This wall is positively charged. This wall is negatively charged. So of course, there will be an electric field existing. I'll draw it here for your convenience. This electric field, which has been given to us as E, right? Capital E. Okay. There is some electric field E which exists between the vertical sidewalls. Uh, okay, so the time, so the question that is asked to us is the time taken by the block to come to the lowest point of the inclined plane. It starts from here and the time taken to traverse this distance, okay? Traverse this lowest point of the inclined plane is how much? Assuming the surface to be smooth, okay? This height is h, okay? So as usual, first let us start by drawing the FPD of this block, okay? Again, so I'll keep a figure and I'll draw the FPD, okay? Okay, so let's first, the block is on an inclined plane, okay? I complete the inclined plane first. Okay. Okay. So here we have our inclined plane and the block is sitting here, okay, on the inclined plane. Mass M. Okay. Now, very first of all, it will have its own gravitational pull. Okay. This mg. I'll use a slightly lighter one. Okay. This is your mg. Okay. Now we have an electric field. Okay. And this is positively charged. So the force will experience an electrostatic force in the direction of the electric field. Okay. In this way, it's experiencing QE. Okay. And as we pointed out that this is a non-inertial frame of reference. So if we talk about an observer who is sitting inside the elevator, we will have to add a pseudo force. Okay. Pseudo force whose direction would be opposite to the direction of motion of the elevator and is an A naught. Okay. So these are the possible forces that are acting on this body. And we need to find actually the time which it takes to traverse this distance, this whole distance. This length is given to us as h, right? This length is h, and this angle is 30 degrees. We need to find the time it takes to traverse this distance. So if I take or find out the net acceleration in this direction along this sloping plane, then I can easily apply my equations of motion, right? S equals ut plus half at square. U is 0. It starts from west from here. So basically it would be S equals half at square. From that I can easily find the t. Okay. For that I need to find the net acceleration along this slope. So obviously I'll start breaking the process into its components, right? First I'll start with this MA naught. This is 30 degree, this is 60 degrees, right? This angle is 60 degrees. Okay. I'll write the components in yellow color. Okay. So I break this force. Sorry. I break this force, okay, into components. It would be MA cos 60, that is sine 30, that is half MA by 2, and along perpendicular. But I don't actually need the perpendicular component here because essentially I just want to know the resultant acceleration along this inclined plane, right? I would have needed this perpendicular component when I would find the normal force and if there would have been a friction given. If the friction value would have been given, the coefficient of friction, then I would have needed to find the normal force. And again, that mu and have been a frictional value. But this is a smooth, right? It is a smooth inclined plane, so I have no friction. So I don't essentially need the normal value. Okay, so just to avoid confusion, I am not considering here our uh, this normal component. Okay, so I resolve this MA not. Okay, all right. Now let's come to this electrostatic force. Okay, this electrostatic force, this angle should be 30 degrees, right? So its component would be to this direction. Okay, and it would be QB cos 30, right? Which is root 3 upon 2. So root 3 QE upon 2. Okay. And in the same way, it would also have a normal component, which is QE by 2, but we don't need it here. So I'm not writing the unnecessary points. Okay. All right. So I omitted again this. Now again, I'm just left with this mg, right? Mg is similar to just like this n a naught, right? So I can just break it like this as mg by 2. All right. So great. And this block had a mass of m. So the F net, let's take it over a new page. Okay. This is the FPD. Okay. So the F net, the F net would be along this direction, the block has to travel from here to here. So along this direction, that is mg by 2 plus ma naught by 2 minus this root 3 q by 2. Okay. It would be mg by 2 plus ma naught by 2. So ma naught is g by 2. Okay. Minus root 3 q by 2. Okay. And this is equals to mass times the net acceleration. Okay. From Newton's second law of motion. So the net acceleration down the inclined plane, the smooth inclined plane, would be the net acceleration would be F net upon M, isn't it? So that would be equal to uh, M A naught plus G minus okay, QE. Okay. Now we need to find this length. Okay. If this is H. Okay. And this is suppose I say L. Okay. So L sine theta would be H, right? So H is or L upon 2. So L is 2H. Okay. So if I write S equals UT plus half AT square. Okay. Now this U value is 0. Okay. Because it starts from rest at the top of the inclined plane. This S is just L, which is 2H. Okay. So 2H is half AT square. That implies T would be 2 times of under root H upon A, right? And we substitute the value of A from above, which is H 2m goes above and M A naught plus G minus the Q. Okay. So if you check the options, I guess, yeah, the C option comes out to be absolutely true. Okay. So this is the answer to this question. Yes, this was pretty easy for JEE level preparation. It's just a basic kinematics and Newton's laws of motion basically. You draw the FPD and you calculate the time taken down the street. Okay. Things would have been a bit more trickier if we would have added a normal component and a frictional surface. Then there would be a mu n component here. So okay. So I guess this question is also clear to everyone. And there should be no doubts in this question. Okay. Okay. Now let's move on to the next question. Okay. Uh, let's read out the question first. A proton of mass m and accelerated by a potential difference b gets into a uniform electric field of a parallel plate capacitor parallel to the plates of length L at midpoint of its separation between the plates. So we are this being said that let's draw the diagram. This is actually a similar question from S.C. Verma's example, solved examples. Okay. We have a parallel plate capacitor over here. Okay. Whose side length is L. Okay. And we have a proton of mass M, which is accelerated by a potential difference V. So its energy, the energy is, yeah. So its energy is uh, half mv square, let's say. Okay. And which is equals to qv, right? And what is q? That is ev. Okay. So from that we can find out the velocity as 2ev upon m square root. Okay. So it enters this parallel plate capacitor, the uniform electric field of a parallel plate capacitor parallel to the plates of length L at midpoint of its separation between the plates. So these plates are separated by some distance, okay, and at midpoint of that distance, this proton enters, okay. Let me draw a bigger diagram. Okay, this is a parallel plate capacitor we have, okay, of side length L, okay, and the proton enters here at midpoint of the separation between the plates, okay, at velocity v, okay, which is given by this, okay. Or if you are confusing it with the v in the expression, let's take it as u, okay. Let's take it as u, okay. All right. Now, okay, the field strength in it varies with time as E equals AT, where A is a positive constant. Okay. This has some electric field in between the two plates, of course. Okay. This is the electric field between the two plates, which is E equals AT, right? So it's directly proportional to the time. Okay, time elapsed, where A is a positive constant. Find the angle of deviation of the proton as it comes out of the capacitor. Okay, so you just assume that it does not collide with any of the plates. Okay, now you just imagine that it entered like this, and this has an electric field like this. So at each point of its path, it's going to experience a upward force. Okay, so its y-axis velocity would be increasing. Okay, and along the x-axis, we don't have any force, so this u will remain constant in the x-axis. So this proton would undergo a path like this. It would undergo a parabolic path and emerge at this point. Okay, if I draw its path out, it will follow a parabolic path, right? It will follow a parabolic path out here, and it will emerge out, okay, with some velocity v, let's say. Okay, we need to find this angle of deviation. It entered like this, it's leaving like this. So what's the angle of deviation? This angle we need to find. Okay, in this direction is of course still u. Okay, now, so for finding the angle of deviation, if we find this, we know this should remain u. Okay, If we find this perpendicular component, okay, then we can take this tan theta is the perpendicular component upon the parallel component, right? Then we can find the inverse of that. And also you can see in the options that we have tan inverse, okay? All right. So this has to now traverse a distance of L, okay, at speed U, which is constant. So what is the time that is taken? Okay, the time taken actually inside the capacitor is L upon U. Okay, this is the time taken. Till this time, it's under the influence of this electric field. Okay, so what is the acceleration in the perpendicular direction? It would be QE upon M, right? It is QE. What is E? Which is AT upon M. Okay, this is the perpendicular acceleration. And for this much time, it's there. And initially, this velocity, this u perpendicular, the initial velocity in the perpendicular direction is 0. Okay. Now you can apply v equals u plus at, right? Remains for time, capital T in the influence, which is equals to u is this is 0, a perpendicular, which is EAT. It's this E. This thing, this is actually at a particular time. Okay, so this velocity is actually coming as a function of time. Okay, which is EAT upon M. Okay, into dt. Okay, so this thing would actually represent a change in velocity. Okay, to represent change in velocity as a function of time is this. Okay, so uh, yeah, or you can this change in velocity, you can write it as dv, right? Dv is EAT upon m into dt. Okay, EAT upon m. So is EAT upon m dt. Okay, so now you have to integrate both sides. Okay, initially it was 0. Final, we need to find v perpendicular. Initial time was 0, and finally it traveled for a time capital T. Okay, so we'll have v perpendicular is equals to E A upon 2m into t square, right? Which is okay. Let's just keep it like this is the value of the perpendicular velocity, and the parallel velocity we had, which is u. Okay, and the parallel velocity is still u because it's not affected by any force. Okay, and u is we found out here square root of 2ev on m. Okay, now if I take this tan theta for this angle of deviation theta, if I take the tan theta, this will be perpendicular. It will be v perpendicular upon v parallel, right? V perpendicular upon v parallel, which is EA upon 2m into root of m upon 2EV e square. Okay, and we have T is L upon U again. So this is L square upon U square. Okay, what is U square? this. Okay, so I write U square as 2EV upon M. Okay, so if I simplify this, this would be just 3 over 2, okay, of this term. This would be 3 over 2, okay, and this L square just comes over here, okay. So now we have this all cancellations over here. So yeah, which is this A L square root M upon 2 into cube root of into the square root of 8, okay, 2 root 8, and this is 2 root 2, so it's basically 4. Okay? This would be 4 E 3 by 2 upon E, which is root E, okay, root E B raised power 3 upon 2, okay, which is A L square upon 4. I take everything under the square root. I'll get M upon EVQ. Okay, so I get tan theta as this tan theta as this. Okay, so I'll get theta finally. Theta I'm writing over here is tan inverse of A S square upon 4 into M upon EVQ. Okay, so tan inverse A square upon 4, A square upon 4 and root M upon EQ. Okay, so this is the answer to this question. Okay, you should actually practice this question because you should have a knowledge of this type of question, this deviation, because this is one of HC Verma's illustration format question. Okay, and you should be thorough with HC Verma because that direct sort of questions come in JEE mains. Okay, that's why I'm taking up this exam. Okay, fine. I guess everyone is clear with this question. Then I hope we can move on to our next question for today. Okay. All right. So we are going till now, guys. Let's move on to the next question. This. So we have been said, okay, that two identical beads over here have a mass m, okay, and charge q. These two have charge q. When placed in a hemispherical bowl, this is the hemispherical bowl of radius r, okay, with frictionless non-conducting walls, the beads move, and at equilibrium, they are at a distance r apart. Then this is an equilateral triangle form. These beads ultimately they were like this and they move apart, okay? Because they are positively charged, similarly charged. Okay. The charge on each bead is it's asking the value of Q. Okay. What should be the charge on each bead? So I guess again this is a pretty easy question. Uh, we'll draw the FBD for a single bead. Okay. Let me color this first. Okay. All right. So I have a bead here. Okay. What all? forces should act upon it. First, it will have its own weight. Okay. Now, this will again have its electrostatic repulsion. Okay. Which is, let's say I have the charge is given as Q, right? K, Q1, Q2 upon R square, right? And perpendicular to this surface, it will experience a normal, okay, along the radial direction. Because if this is a hemisphere, then perpendicular will be just along the radial direction, okay? So along the radial direction, it's experiencing a normal force, okay? And uh, it's experiencing a normal force. And I draw this normal with the vertical, okay? And if I say this angle, okay, this angle is theta, this will be and cos theta, and this will be and sin, okay? So from here you can see n sin theta should be equal to this and cos theta should be equal to this, okay, for equilibrium. All right. So if I directly write tan theta from here, okay, should be tan theta is q square over 4 pi epsilon naught r square upon this, right? Okay, on this. Now let's see what is the theta. Okay, I said that this is normal to the vertical and this is theta, I said. Okay. Uh, yeah. So I said this angle is theta. Okay. Then this is 90 minus theta. And as this forms an equilateral triangle with sides as r, this is 60 degrees. So this has to be 30 degrees, right? So theta is 30 degrees. This tan 30, which is 1 over root 3, right? We need to find Q. So Q is mg over 4 root 3 pi epsilon naught. Oh, sorry. Everything goes better, right? Q is 4 pi root 3 pi epsilon naught r square mg whole square, right? So this is the value of Q, okay? So, and if you take 4r square outside, it will be 2r, and in the square root, we'll have pi epsilon naught mg over root 3. 2r pi epsilon naught mg over root 3. So, C option would be your correct answer. Okay, I guess this question is also pretty easy. Again, the concept on the free body diagram. Okay? All right. So, guess this is pretty clear to everyone. Okay. Let me check the comment section for once if you have any doubts from any students. Let me check the comment section for once if I We don't seem to have any doubts currently. So that's great. So let's move on to our next question, okay? Which is, okay. Now this is a multiple option correct type question. Let me tell you from the beginning, okay? This is a multiple option correct type, okay? Could be one or more than one option correct. It's a JEE advanced type of pattern, okay? This is a multiple option correct type question. So yeah, let's read out the question first. We have an infinite non-conducting sheet of negligible thickness, okay, this one, carrying a uniform surface charge density minus sigma, okay? And next to it, we have an infinite parallel slab of thickness D. This is the uniform parallel slab, okay? Thickness D with uniform volume charge density rho, it is plus rho. All the charges are fixed. This is fixed and this is also fixed, okay? So we are being asked, okay, that the magnitude of the electric field at a distance h above the sheet from here, okay, is this much. Magnitude of electric field inside the slab at a distance h below, okay, is this much. Magnitude of electric field at a distance h below the bottom of the slab, again, same option. Magnitude of electric field at a distance h below the bottom of the slab, sorry, bottom of the slab from here, bottom of the slab. Okay, all right. So let's first check the first option. Okay, let's check the option wise. Okay, let's check option wise. For everyone should know this. Okay, that the electric field due to the sheet of charge, okay, is given by sigma over 2 epsilon naught, right? For infinitely long charge sheet, okay? And since it's given as minus sigma, so I'm writing minus sigma, okay? And the electric field, it was slab. How to make it easy, okay? Let's see. This is the slab, okay? Now, if I just take it analogous to the sheet has negligible thickness, okay? But this slab has some thickness, which is given D, and its whole volume density is rho. Then if I just consider it analogous to this uh, sheet, then what would be the surface charge density of the slab? It would be just rho D, right? We just need to get eliminated this D. Rho D would give the surface charge density of the slab if it were analogous to a sheet, okay? So it will just be again sigma over epsilon not only, and in place of sigma, I'll write as rho D. Okay. So these two things you need to understand first. Okay. Now, at a distance h above the negatively charged sheet. Okay. From here, we need a distance h. Okay. This field doesn't depend on the distance from the sheet. Okay. Because these are considered as infinitely long. Okay. So the net electric field should be this the sum of these two. Okay. Just rho d minus sigma upon 2 epsilon naught, okay? Rho d minus 2 minus sigma upon 2 epsilon naught, okay? And is that option? Yeah. So option A we have correct. Okay, let's move on to option B. Okay, now at a distance h below the top of the slab. Okay, at a distance h below the top of the slab. Now, how do you find this thing? Okay, let's just understand the thing. I have this slab. Okay, and what I do is at a distance h. Okay, a distance h below I pass a line. Okay, this thing is h. Okay, so this whole is actually rho. Okay, so the sigma for this top part will be rho into h, right? It's rho into h, and this will be rho into d minus h, right? And this is suppose both are same charge, right? So at this point, or at this level, we have two blocks. Okay, this top one, and this bottom one. Due to this top one, let's say this is positively charged, it will be directed in this direction. And due to this bottom one, it will be directed in this direction. But this bottom one is larger, okay, because let's assume that this bottom one is larger. So the net one will be towards this direction. So with this minus this, okay, which is uh, rho into d minus h upon 2 sigma, right? For this block or this slab minus rho h upon 2 sigma, which is the rho into d minus 2h upon 2 epsilon, okay, along this direction. And as usual, we have the slab over here, okay, of minus sigma, okay, and so this will just get added up over here, which is sigma over 2 epsilon naught, okay. So the net electric field would be, in this case, in option B, the net electric field would be this the sum, right? Net electric field is rho into d minus 2h upon 2 epsilon naught plus uh, sigma over 2 epsilon, okay, which is sigma plus rho d2 minus 2h upon 2 epsilon naught, okay. 2 epsilon naught is the LCM. So it is sigma plus rho into d minus 2h upon 2 epsilon naught, okay. So now this option is also correct. Now, magnitude of electric field at a distance h below the bottom of the slab. Now, this is easy. Below the bottom of the slab, it's just like the first case, right? Below the bottom of the slab, this is the slab, okay? This is the slab, and I have this minus sigma, okay? And it has a distance h below the bottom of the slab. So from here at distance h, we are being asked the electric field, okay? So, and this is rho, okay? This is d. So it would be rho d over this minus sigma over 2 epsilon naught, right? So rho d minus sigma over 2 epsilon naught, not the negative side, okay? It's directed towards this side only, and this side we're taking as positive, okay? This positive, so we're taking this side as positive, okay? So A, B, and D are our correct options, okay? So this is a multiple option correct type question, where A, B, and D are correct options, okay? So I guess everyone got this. You just need to know this formula, okay? You have to keep in mind this formula, okay? So I guess rest all is just calculation, okay? All right. So let's move on to next question. I guess everything is clear up till now. So the next question is a comprehension type question, okay? So we have been said that two positive point charges, each of magnitude q, are placed on y-axis at points 0, comma a and 0, comma minus a. So I have the axis system, okay? And the axis system like this. And at 0, comma a, sorry, it's on the y-axis. 0, comma a, okay? And at 0, comma minus a, okay? We have two positive point charges, each of magnitude q. Okay, this magnitude is q. Okay, a positively charged particle of charge q naught and mass m, when displaced slightly from the origin in the direction of negative z-axis. Okay, and I have another positive charge at the origin. Okay, q naught mass m. Okay, displaced slightly from the origin, it will, of course, it will be repelled by the positive charges and it will just shoot off. Okay, attains a speed v naught at infinity. Okay, at infinity, its speed is v naught. Okay, now when the particle is projected towards the left along the x-axis from a point at a large distance towards the right of the origin with a velocity half of the value of v naught, then it comes to rest at a point p x, 0. When the particle is projected towards the left, okay, along the x-axis from a point at a large distance towards the right. The point is at a distance towards the right, and from here it's projected to the left. It comes to a rest at a point p x, 0. Again, if a negatively charged particle from the rest, okay, it is at a very large distance towards the left of the origin, then this negatively charged particle crosses the origin with a speed v. Based on the above facts, answer the following question. So let's first the value of v naught is. So from this diagram first, we should know that uh, here we'll first find the potential energy of this system of charges. We'll apply conservation of energy over here. Okay. The kinetic energy is zero, and here at infinity, the potential energy will be zero. Okay, because it will be upon infinity, and here the kinetic energy would be half mv naught square. Okay, So we'll apply first the energy conservation over here. We have identical this one system. Okay? So it will be 2 times Q, Q naught over 4 pi epsilon naught. Distance is A, right? This distance is A. Okay. Plus 0 kinetic energy, which is equals to half and V naught square. Okay. So you'll find V naught as square root of 2. This cancels. So Q naught over pi epsilon naught A. M, M A. Q naught over pi epsilon naught M A. Okay. So this option is correct. Next, the value of X is, okay, for finding X. What was the question saying? Uh, when the particle is projected towards the left from a point along the x-axis at a very large distance. Okay, so this is at infinity here. Okay, from a very large distance is again projected with the velocity v naught by 2. Okay, then it comes to rest at a point x comma 0. It comes to rest at a point x. Okay, from here it's x. Okay. Again, we'll apply conservation of energy here. It's a very large distance, so it will have only kinetic energy expression. Okay, so it will be half mv naught square equals this potential energy, right? This distance is under root of a square plus x square, right? Okay, so it's two body system again. So 2q naught over 4 pi epsilon naught A. 4 pi epsilon naught the distance, which is this. Okay. Square plus A square. Okay. And B naught square from here we can put in. Okay. Okay. So half m q naught over pi epsilon naught m A is 2q naught over 4 pi epsilon naught under root of square plus A square. Okay. So let's cancel out first. So Q naught is cancelled. Pi epsilon naught is cancelled. Okay. Uh, and this M to M is cancelled. We're just stuck with A here. 2 upon 4 is cancelled, which is 1 over 2. And 2 to 2 cancel also. Okay. So we are just left with uh, this here, which is x square plus A square is 16A square. That implies x would be root 15A. Okay, would be root 15A. Okay, guess you understood the basic concept over here. Just equate the energies. Okay, that is conservation of energy. Okay, now say a negatively charged particle from rest and at a very large distance towards the left of the origin. Okay, from here, from connecting the left of the origin. This negatively charged particle crosses the origin with the speed v. Okay, so here it reaches and crosses with the speed v. Negatively charged particle, of course, it will be attracted by this positively charged. Okay, that's why. So at infinity, it will just have this kinetic energy. Okay, is half m uh, the negatively charged particle from west. Okay, so this total energy is zero, the infinity. Okay, and this equals half mv square minus 2 q naught over 4 pi epsilon naught a. Okay, guess everyone is uh, comfortable with this. Equals q naught over 2 pi epsilon naught a. Okay, so this 2 to 2 again cancel. So you will get v as q naught over pi epsilon naught a m double is the same as v naught, right? So the value of v is the same as v naught, right? Okay. I guess this question is also clear to everyone, right? Great, guys. Till now, we have understood many good questions actually. Okay. So let's move on to the next question. This is again a comprehension based question. A region in space contains a total positive charge Q that is distributed spherically such that the volume charge density is given by alpha for r less than r upon 2 and this for r upon 2 to r. That this basically means I have a spherical charge distribution. Okay, I have a spherical charge distribution. Okay, and this spherical charge distribution is itself divided into two regions. Okay, this is itself divided into two regions. One is still r upon 2. Okay, from the center till r upon 2 and from the center till r. Okay, this space. So this space has alpha as the volume charge density, and this in between space is 2 alpha into 1 minus r upon r. Okay, r is any arbitrary distance from the center. Okay, all right. And the total charge contained in this volume is given to be q. Okay, and for r more than r, the outside of this sphere is 0. The fraction of total charge contained in the region this. Okay, so let's find first, you know, our q. Okay, our capital Q. Capital Q would be here it's constant volume density, that is alpha. So alpha into 4 upon 3 pi uh, r by 2 q. Okay, plus this in this space it actually varies with the distance. Okay, so you can't directly do this. We have to apply our integration. Okay, so we'll have to apply our integration over here with this plus integral from R by 2 to R, the volume charge, which is this much, okay, into the element, okay, this 4 pi R square dr. What did we do? We went to a distance smaller and I considered a strip, a spherical strip of radius dr. Okay. So its volume would be the surface area, which is 4 pi r square into the thickness, which is dr. Okay. So 4 pi r square dr is the infinitesimal volume multiplied by the volume slash density integrated from the region r upon 2 to r. Okay. So, okay. And we have been asked that the fraction of the total charge in this region, fraction of, so this is what fraction of this. Okay. So it's asking basically this. So if you solve this, this comes out to be pi alpha r cube over 6 plus 11 upon 24 pi alpha r cube. Okay. So the fractional charge, okay, is what? This upon this sum, right? Which is pi alpha r cube upon 6, okay, divided by this sum, right? Which is 24 upon, no, uh, yeah, 24 upon, here it would be 6, 4, right? 4 plus 11 into pi alpha r cube. So this is cancelled. 6 fours are 24. We'll get it as 4 upon 15. Okay. This is the fractional charge. Okay. So 4 upon 15 is the right answer. Okay. Well, now the second bit, if an electron is placed at the center of this arrangement and slightly displaced, then it will execute SHM. A time period of oscillation, assuming it is less than R upon 2. That is, it is within this sphere. Okay. So, yeah. Uh, if an electron is placed within this region, okay, this is a solid sphere, we can assume, okay, with a density rho. So the electric field, first of all, is rho r upon 3 epsilon naught, right? In this case, this rho is alpha. If it's uh, displaced by distance x or what is given, it will slightly displaced by a distance x, okay, upon the epsilon naught, okay. What is this electric field? So that implies this force is q alpha x over p epsilon naught, which is ma. So a would be q alpha x over 3 m epsilon. Okay. So we can see that a is directly proportional to x. So it is a simple harmonic motion. Okay. And this expression is omega square, right? The coefficient of x, q alpha 1 p m epsilon naught. Okay. This is omega square. So the time period is 2 pi upon omega, right? Which is 2 pi Cm epsilon naught Q is E late upon uh, E alpha, right? And okay, but in the options we are being asked in terms of capital Q, right? And if we write capital Q, it was 15 upon 24 pi alpha r cube, right? And so we need to get rid of this alpha, right? So from here, alpha is 24q over 15 pi r cube. If I put it here, 2 pi under root em epsilon naught over p into alpha. Alpha is 24q 15 pi r cube. Okay, so 3 8s are 24. Okay, so if you solve it, uh, this 3 cancelled, we'll have 8. Okay, so 5 under root 15 and 8. 15 and 8. Okay, numerator 15, denominator 8. Okay, I guess this question is easy. Okay, and the electric field in the region, this region, what's the electric field? This is a spherically symmetric surface, so we can easily apply Gauss law over here. Okay, I'm erasing this part just for now. Okay, just for this. Okay, so we can apply Gauss law. Okay, which is integral of surface integral of E dot dA is the net enclosed charge over epsilon naught. That is Q1. I take Q1 as this one, the charge enclosed in this, plus some region of this bigger one, right? So it is Q1 plus integral from R upon 2 till small r, 2 alpha over epsilon naught, 1 minus 4 pi r square dr. Okay, and this Q1 value we found out 5 alpha r cube over 6, right? Plus integral r upon 2 to r 2 alpha over epsilon r 1 minus r over r over 5 r square dr. Okay, and this E dot dA is E into 4 pi r square, and if you solve this integral with the proper limits, you actually end up with uh, minus 5 alpha r cube over 24 epsilon naught is 8 pi alpha over 3 epsilon naught to 1 minus 3r over 4r r cube. This is the solution of this integral with the proper limits. Okay. Not a busy job. You can break this bracket 4 pi r square and this r they multiplied over here and put the proper limits. Okay. Just a calculation based. And from this, you can find ultimately E, E will come out to be minus uh, this r square plus 2 alpha r over 3 epsilon r 1 minus 3 r 4 r. Okay. So if you compare, that is option number D in the question. Okay. Nothing difficult. This seems the options appear seem to be difficult, but actually the concept is pretty simple, right? Just a hollow and the solid spherical charge. Okay. All right. I guess this is easy. Over. And yeah. So let's move on to the next question for today. We are saying, okay, we are saying there is a charge of plus Q which is uniformly distributed, okay, in a spherical volume. Okay. This charge is uniformly distributed in a spherical volume of radius capital R. A particle charge plus Q and mass M is projected with a velocity V naught from the surface of the spherical volume. First, I have a spherical volume. Okay. And I have a tunnel inside this spherical volume. Okay. I have a tunnel inside this spherical volume passing through its center. And here I have a particle of Q mass M projected with a velocity V naught. This charge is plus Q, okay, and this radius is R. Okay. So find the minimum value of V naught such that it just reaches the center. Just think that this is a positively charged and this whole sphere is also positively charged. So while coming, it will experience repulsions. Okay. So it just reaches the center. That means it decelerates and slowly comes down to rest over here. Okay. Just reaches the center. Assume that there is no resistance in the particle except electrostatic force. Okay. So again, we can apply conservation of energy over here. Here the total energy and here the total energy. Okay. So total energy at the surface would be first the kinetic energy half m v naught square, okay, plus q into the potential at the surface, right? What is the potential at the surface of this sphere? It would be q over 4 pi epsilon naught into r, right? And it just comes to the center, so the kinetic energy is zero. As at the center, the potential energy is 3 by 2 times of the 3 by 2 times of the surface, right? Okay. Solid sphere. So from here, you find V naught square. Yes. 3 by 2 times this minus this. It is 1 by 2 times. 1 by 2 times Q over KR. Okay. So this 2 to 2 cancel. So V naught would be the square root of QQ over 4 pi epsilon naught MR. QQ over 4 pi epsilon naught MR. That is option number D. Okay. Yes, this is again easy question. Conservation of energy, right? All right. So let's move on to the next question. Because this is pretty easy. Everyone must have got this question. Okay. Let me check the YouTube for a moment. If anyone has any doubts. Uh, not till now, there are no doubts in the live chat. That's a pretty great thing. So yeah, let's now move on to the next question for today. Okay. This question is actually a star question. This question will attempt at the end. Okay. Trust me, you will enjoy solving this question. This is not your classical JEE type question. This is from an advanced book, Introduction to Electrodynamics by Griffiths. Okay. Introduction to Electrodynamics. This is a standard book of electrodynamics by Griffiths. We'll solve this. This is based on Gauss law. We'll solve this at the end. We'll really enjoy solving this problem. Okay. Let's just move on to the next question. We'll keep this to the end. Okay. Now, this question, uh, okay, we'll solve this question. Okay. This is a very, very nice question, very conceptual question. I can guarantee you will take a lot of your concentration and energy. So just give a reading to this question while we take a uh, 5 minutes break. Okay. Uh, take a 5 minutes break and we'll start solving this question. I promise it's a very, very great and conceptual question. We'll enjoy solving it. Okay. Let's take a break of 5 minutes. Okay. Okay, guys. So the timer is up. I hope everyone is fresh now. So let's start with this great question. This question is at my heart actually. So very, very good question. Let's first read it out. Uh, we have a parallel plate capacitor. Okay. This is the parallel plate capacitor. It is made up of two square plates of size A. Okay. So the uh, area is A square, right? Of each plate. The area is A square. Now, the distance between the plates is D. This distance is D. Okay. A dielectric slab of dielectric constant 4 completely fills the gap between the plates. This is the dielectric slab and it fills the space between the plates. One end of the slab is connected to a massless spring of spring constant K. Okay, this is one end of the spring and it is connected to a spring of constant K. Okay, the other end which is fixed. Okay, this end is fixed over here. The mass of the slab is M. Okay, initially the spring is unstretched. Okay, the spring is at its natural level. A constant force F naught is applied to the slab. We squeeze this spring. Okay, we apply a force F naught. Prove that the slab will execute simple harmonic motion. It will get displaced. It will come back again. It will go again. It will execute simple harmonic motion. You have to prove that and find its amplitude and time period. Okay, this is actually a very, very good question. I mind you. Okay, so let's solve it first. First, if I think that if I apply a force, it will get displaced by some distance, let's say x. Okay. So if I draw a new diagram, okay, this is the parallel plate capacitor, okay, and this has been displaced, okay. This has been displaced, this block, okay, by some distance x, okay, by some distance x, okay. This is a minus x, right? Okay. So if you see this capacitor now, it's actually made up of two parts now. This part is vacuum and this part is filled with the dielectric. Okay. So the equivalent capacitance, if I say, okay, these two caps, this can be considered, this is one capacitor till this part, and this is another capacitor till this part. Okay. So these two are in parallel, and in parallel the capacitance just gets added, right? And what is the formula for capacitor? It is epsilon naught A over D. Okay. It's just electrostatics chapter, so I'm just saying the formula epsilon naught A over D. Okay. So what will be the equivalent capacitance? Capacitance for this plus the capacitance of this. Okay. It is epsilon naught. The area, this is x. Okay. So it will be x squared. This area of the plate. Okay. Epsilon naught. Uh, Epsilon naught. No, sorry. This length is x. But again, inside it, the breadth is still A, okay? So it will be A times X, okay? Over the separation is D plus. If we introduce a dielectric, the capacitance actually becomes K epsilon naught A over D, okay? So it will be K which is 4. We have been given dielectric constant is 4 epsilon naught A minus x into A minus x into A over D. Okay. So if you solve this, okay, if you add this and solve this, you get the equivalent capacitances epsilon naught A over D into 4A minus EX. Okay, this is the equivalent capacitance. Now, between these two parallel plate capacitor, there would be an electric field. Okay, and when this dielectric moves, it actually crosses the electric field, and because when the dielectric was just completely filling it, the capacitance was different. So the potential energy stored in the capacitor was different. Now, when the dielectric moved, the equivalent capacitance changed. So the potential energy changed. And you know that if the potential energy is changing, then there is some force acting. Okay. And that force will act upon the dielectric. And that force is du by dx. Okay. Du by dx. It is the magnitude of the force. Okay. Which is, and the potential energy stored in a capacitor is half CV squared. Okay. C is C equivalent over here. Okay. So V is constant. We are maintaining it. So this essentially turns out to be this. Okay. This essentially turns out to be half dc over dx. And we have this C expression over here. We can find dc over dx. Okay. So this turns out to be 3 over 2 epsilon naught A V square over D. Okay. And this always acts inwards. Okay. If this dielectric has been moved away, this force will act inwards. Okay. All right. Now we are applying this F naught here, and this spring is also compressed by distance x, so it will also put kx force. Okay. So the net force, the F net, if I ask, the net force on the dielectric would be F naught to the right minus kx to the left minus this F electric, this electric force or the electrostatic force also to the left. Okay. A B square upon B. Okay, this is the net force. Now we are being set that to prove it will execute a SHM. Okay. In SHM, we always have a equilibrium or a mean position, and at that mean position, this F net is actually 0. Okay. So from that, we find the value of x. Okay. The value of x would be 1 over k into F naught minus p by 2 epsilon naught a b square over d. Okay. This is the value of x that is displaced. Okay. And from the equilibrium position, this much has been displaced. So this is the amplitude of oscillation. This is the amplitude of oscillations. Okay. So we are done with this part. Okay. We are done with the amplitude part. Okay. Now, this is the equilibrium position. Okay. Now, if the slab is further displaced by x naught, okay, this is the equilibrium position x, okay, where the net force is zero. Again, if I displace it by x naught, by a small distance x naught from the equilibrium position, only the spring is getting compressed more, okay, by kx naught, okay. Only the spring force will increase. This F naught is remaining constant, okay, and this electric force is not depending on the displacement or the x, okay. So this and this is remaining constant. Only this value will increase to the left side, okay. If the slab is further displaced by x naught, only the spring force will increase. Other two forces are constant. Hence, the net restoring force in all SHM, we always find the net restoring force back to the equilibrium position will only be what? The spring force, because the other two forces are constant. They are not varying. Okay. Which is directly proportional to the displacement x naught. Okay. So ultimately we'll just have the time period as, okay, so this k is omega square, right? So time period would be 2 pi under root m over k. We know the basic formula, right? So this is the answer and this is the answer. Okay. And because of this being directly proportional to x naught, it will execute an SHM. This is also true. Okay. The main thing was just to find this mean position, okay, of the amplitude of oscillations. Okay, this is actually a very good question where you need to think in lines of this, finding the equivalent capacitance, okay, and finding the electrostatic force that acts on the dielectric. Okay, it's actually a very good question. All right, so I guess everyone is comfortable with this question. Then we can move forward. Okay, all right. Again, a good question. There are, okay, total of 8 point charges of magnitude q which are arranged to form the corners of a cube of side length L. I have a cube, okay, I have a cube over here, okay, and okay, so I'm having a cube, okay, and at each corner of the cube, okay, at each corner of the cube, I'm having a charge of magnitude q, okay, here, here, at each corner cube, I'm having a charge of magnitude q. Okay, q, q. I'm not writing again and again. You understand that? Okay. So, okay, of side length L. Okay. Now, the arrangement is made in such a manner that the nearest neighbor of any charge has the opposite sign. I mean, if I say this is plus q, okay, this is plus q. The nearest neighbor, that is this is the nearest neighbor and this is the nearest neighbor. And These three are nearest neighbors for this charge. They have the opposite sign, that is minus q, minus q, minus q. Okay. Now for this charge, this is the nearest neighbor, this is the nearest neighbor, this is the nearest neighbor. So this has already opposite sign, so these two will also have opposite sign, that is SQ, right? For this charge, this is the nearest, this is the nearest, both have positive signs. This is again a nearest, so this will also have SQ. For this charge, this is nearest, both are positive. This is nearest, this is also positive. This is plus, its nearest should be minus q. Okay, so we have arranged all the charges first of all. Okay, now initially the charges are held at rest. If the system is left free, we are holding it by hand, suppose, and we release it. Okay, if the system is let free to move, what happens to the arrangement? Does the Q shrink or expand? Okay. Calculate the velocity of each charge when the side length of the Q formation changes from L to N times of L. Okay. And assume that the mass of each point charge is M. Okay. Now, let's first make uh, pairs of charges. Okay. We have, okay, we have 12 pairs of Q and minus Q. See, Q minus Q, 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 then Q minus Q, Q minus Q, minus Q, Q, okay, minus Q, Q, minus Q, that is diagonally opposite charges also we'll consider. So we have 12 pairs of Q and minus Q at a distance of L. 12 pairs of Q and Q and minus Q and Q, that is like charges at distance root 2L. Q, Q, distance root 2L, okay? And 4 pairs of Q and minus Q at distance root 3L, that is diagonally opposite, okay? These three. And yeah, this one. So 4 pairs of Q and minus Q at a distance root 3L. So these are the pairs possible, okay? So if I find the total potential energy, 12 pairs of this this thing, okay? Okay, okay. This again another 12 pairs of this thing. Then 4 pairs of this thing. Okay. This is the net potential energy of the initial system. Okay. Now let's say that there is decrease in side length. Let's assume for 1 second. If I decrease the side length, if I add all this, first of all, the value of u comes out to be minus q square over pi epsilon naught L into 3 root 6 plus root 2 minus 3 root over 6. Okay. Now, just see, these are attracting each other. Okay. These are just attracting each other. So overall, the cube size should shrink. Okay. Also, with decrease in the side length, the potential energy will decrease. Okay. With decrease in side length, as this is a negative sign, so the overall potential energy uh, should decrease. Okay. Therefore, the cube should shrink as the conservative forces act in the direction of decreasing potential energy. Okay. Electric field, they are just pulling at each other. Okay. Minus q, q, minus q, q. They are just pulling at each other. So the size, first answer, it is shrink. Okay. First answer is it will shrink. Okay. And then when it shrinks to n times of L, what is the velocity of each charge? It's asking. Okay. So we'll just apply conservation of energy. We have 8 particles with some velocity. Okay. That equals to first the final, the initial minus the final potential energy, because uh, the negative change of kinetic energy is the change of potential energy. Okay. Negative change of kinetic energy is the change of potential energy. Okay. Or a conservative force. So 8 times of the kinetic energy is U initial minus U final. Okay. So that is Q square over 4 pi epsilon naught 3 root 6 plus root 2 minus 3 root 3 over root 6 into 1 minus L minus 1 over L. Okay. So, or in other words, we will have B as the square root of Q square 1 minus L 3 root 6 plus root 2 minus 3 root 3 upon 4 n m pi L epsilon naught root 6. This is the answer. Looks a bit complicated, but actually it's nothing but the conservation of energy only. Okay, from work energy chapter. Just this term looks complicated, otherwise the concept is very simple. Okay, so I guess everyone also understood this question. Okay, so if everyone is comfortable with this, let's move on to the next question. Okay, the next question says two concentric rings placed in a gravity-free region in the YZ plane, one of radius r carries a charge plus q and a second of radius 4r carries charge minus q distributed uniformly over it. And the minimum velocity with which a point charge of mass m, charge plus q, should be projected from a point at a distance 3r from the center of the rings on its axis, so that it will reach to the center of the rings. We have been said that uh, we have two concentric rings. Okay, this is one ring. Okay, inside it we have another ring. Two concentric ring. Okay. Yeah, I guess you understand, right? So we have two concentric rings of radius r and 4r. Okay. Of radius r, 4r with charge plus q and minus 8q. Okay. And the minimum velocity point charge of mass m and charge q. Okay. Should be projected from a point at a distance 3r. Okay. From the center of the rings. Okay. M plus q. With what minimum velocity should it be projected so that it will reach the center of the ring? Basically, if it's positively charged, it will be attracted by this minus 8q and it will be repelled by this plus q. So, depending on the distance, this value will change. So, when this will dominate and when this will dominate. Okay. And if it's asking V minimum, that means you always have to think that when the particle reached here, it becomes at rest or it becomes stationary. Okay. So again, we'll apply conservation of energy over here. Okay. So half m v mean square plus q v initial is 0 plus q v final. Okay. Or you can say that the minimum would be the minimum velocity would be 2q over n v final minus v initial. Okay. Now v initial is this condition only, right? When it is here, this distance would be, this is 3r, this is 4r. Okay. So this distance would be 5r, and this distance, this is root 10r, right? So v initial would be kq over root 10r minus 8kq over 5r, right? V final, and the particle is here. Okay, V final is kq over r minus 8kq over 4r. Okay, so you need to find V final minus V initial. 2q over n. V final is this. V initial is this. So 8q upon r, 1 minus 1 upon 10 minus 8q upon r, 1 upon 4 minus 1 upon 5. Okay, so that equals therefore 2q over m. Okay, PQ upon R. 10 minus 1, 10 minus 20. So 8 over 20 is 2 over 5. So 2 over 5. Okay. And if you solve this, you will end up as uh, the final answer. If you solve this, you will get it as Q over 2 pi epsilon naught mr into 3 root 10 minus 5 upon 5 root 10. Okay, so this is the answer. Answer looks a bit complicated, but again, the concept is very, very simple. Okay, again, it's conservation of energy. Okay, so a great many questions in electrostatics are actually framed based on the concept of conservation of energy. Okay? We have solved a really great number of examples, questions based on the conservation of energy itself. Okay, just to get an idea of how easy the questions are, but just a bit of calculation. Okay, all right. So let's move on to the next question. Okay, this. Okay, so yeah, let's do this question now. Uh, we have a small charge sphere. Okay, mass m charge q is connected by a light inextensible non-conducting string of length L to a fixed point P. Okay, the sphere is just fixed here. Okay, the sphere is at rest in equilibrium at position A. It is free to slide on a non-conducting frictionless horizontal surface. Okay, designated as the OXY plane. Along the x-axis lies an infinite line charge. That sphere is to be imparted a velocity u at a position A, okay, so that it moves in a complete circle about the center P. When impart a velocity u, it moves in a complete circle, okay. BCD are points on the circumference. PD is parallel to line charge. AC is normal to the line charge, okay. So this sphere has mass m, charge q. This is 2L. Okay. It is connected by light inextensive non-conducting string of length L. Okay. The sphere is at rest. Okay. So these are the data that is given to us. First question. The instantaneous tension in the string at that instant where it's given this velocity. Okay. So okay. So what would be the in first due to this line charge? Okay, this is 12. Okay, and okay, this is P is 12, and this is attached here. Okay, so this length is L, of strength of length L to the fixed point. Okay, it is equilibrium in the position A, so it is here. Okay, so this length is PL. Okay, so electric field at A due to this infinite line charge would be electric field at A is lambda upon 2 pi epsilon naught into EL, right? Lambda upon 6 pi epsilon naught L. And this force on this charge would be the times of the electric field times the charge, right? Okay. Now, this is thing like this, and this is the tension will be pulling. Okay. So, put the FPD, the tension minus this force would be this mv square upon r, right? The uh, centripetal acceleration. Okay. So, from that, you get the instantaneous tension as mu square on L plus lambda q upon 6 pi epsilon of L. Okay. So mu square plus this. Okay. Plus the option. Now, the potential difference between the points A and B. The potential difference between the point A and B. Okay. So at any position x at a distance from the line charge, okay, from the line charge, the electric field would be k lambda upon x. Okay, so the change in potential is minus edx, right? So the potential difference between V AB, okay, between V AB is minus integral k lambda dx upon x, okay, EDL, moving from x1 to x2, okay, which is k lambda ln 1 upon x from x1 to x2, which is that is VAB will be lambda over 2 pi epsilon naught ln x2 upon x1, which is 3L upon 12, that is 3 upon 2. Okay. So lambda upon 2 pi epsilon naught ln 3 upon 2. Okay, great. And the tension in the string in the sphere reaches the position B. Okay, and the sphere reaches the position B. Okay, the sphere reaches at the position B. The tension is just mv square upon r, right? And from the conservation of energy, the work done on the charge, that is q times the potential difference between B, is a negative change of kinetic energy, right? Okay. So from here, you get 2qv AP plus m v square minus u square. Okay. So you get P as m upon L u square minus 2q VAB. And VAB we found out. So if you substitute that, you get mu square upon L minus Q lambda upon pi L epsilon naught ln 3 over 2. Okay, because um, this is the answer. E. Okay, because at this point the velocity would be this way, this intention, and this is the mp square upon L. Okay, so T is mp square upon L. Because this question is easy to everyone, clear all the concepts. If you are clear with this, we can move over to the next question. Okay, this question is again a star question. This is from University Physics by Roger and Friedman. Okay, I'll discuss it at the end. I'll just give you hints. Okay, it's just a proof type question. Okay, so I won't go deep in this calculating part. I'll just give you the proof. Okay, I'll just give you the hint to how to approach this question. Okay, so we'll just discuss these star questions at the end. Okay, this again is from the same book, University with University Physics. Okay, it's the great standard book, international book. Okay, I'll give you the intuition about this problem. It's just a proof type question. Okay, so okay, next this Millikan oil drop experiment. This we will solve. Okay, at the end. This is again a star question from your University Physics book. Okay, all right. So these three questions are done. Okay, now this question is actually an Olympiad question. Okay, from the Chinese Physics Olympiad. It's actually a very good question. Okay, so this question, if you attempt, it will be. I have also included all Olympiad and various, standard books questions, so that will be helpful for you to understand how international level also the same concepts apply to all places. Okay, so let's take the question first. We have a negative point charge minus q of mass m, which is currently orbiting a fixed positive charge q at a radius of rotation r naught. Okay, so we have a charge q. Okay, we have a charge q, and at a radius of rotation r naught. Okay, and at a radius of rotation r naught, uh, minus q charge of mass m is rotating. Okay, now what happened? The orbiting charge suddenly disintegrates or explodes such that it ejects half of its mass in the radial direction at a negligible velocity. Okay. Now what happened? The same, it exploded, and this m by 2, half of its mass, okay, it's uh, ejected in a radial direction, okay, with negligible velocity. Okay. However, the leftover mass still retains the entire charge minus q. This is V0 and Q also 0. Now this retains the entire mass, okay, which is still orbiting. Okay. Determine the minimum distance between the leftover charge and Q. Okay. this distance, the minimum distance, okay, in motion thereafter while neglecting any gravitational effects. Okay, pure electrostatic, the minimum that this was R naught, and after exploding, it came closer. Okay, we have to find that minimum distance. Okay, so uh, let's first consider the first case. Okay, you know that the Coulomb's force, that is the K Q1 Q2. Okay, the K Q1 Q2 upon R naught square should be equals to uh, mv square upon R naught. Okay, let's say it's moving at some speed. Okay, so from that we can find your V as Q over 4 pi epsilon naught m R naught. Okay, it's rotating at this much speed. Okay, now the leftover mass is ejected in the radial direction at a negligible velocity. That means it doesn't have any momentum. Okay, this p is zero, so m by 2 by v is zero. So momentum of the leftover mass is zero in the radial direction. So it's explosion, that is internal forces. So no net external force is acting on this particle at the time of explosion. So the momentum should be conserved, and so this leftover charge also, it should not have any change in momentum. It should also, so the radial velocity for this m by 2, this still orbiting, should be zero, but the tangential velocity should remain unaffected. Okay, there should be no change in momentum. So the tangential velocity is still this much only. Okay, the total mechanical energy of the leftover mass now, the leftover mass total mechanical energy is half m by 2 v square and the electrostatic potential energy, right? Okay, this is minus 3 q over 16 pi epsilon naught r naught. This is the total energy, and the total angular momentum is mvr, right? Here it's m by 2. Okay, total angular momentum of the leftover mass just after the explosion. Now, after some time, this came to some closer distance. We say small r. Okay, the minimum distance that we are required to find. Okay. Now, the total mechanical energy and the angular momentum of the leftover masses should be conserved because there is no net torque acting upon it. Okay, it's just under the influence of electrostatic force, which is a central force. So torque is R cross F. So this R is R and F zero. So sine zero is zero, right? So it's a central force. That's why there will be no torque. So angular momentum should be conserved. And no net external force is acting. It's just a explosion. So this net energy should also be conserved. Okay. So we would say m by 2 r naught b should be equals to m by 2 rv. Okay, some tangential velocity at this minimum distance. Okay, some tangential velocity at this minimum distance. Okay, this is the conservation of the angular momentum, and from the conservation of energy, you will have half m by 2 bt square. Okay, minus the potential energy equals to the total mechanical energy. Okay. this. So if you solve these two equations, okay, you eliminate Vt. Okay, this terminal velocity term you eliminate. You substitute Vt from here in this equation, and you will get this quadratic equation for R, right? Where R naught is a constant. So that implies R would be 4 plus or minus square root of 16 minus 12 over 6 times R naught. Okay, from Srivanacharya formula, quadratic equation. Now, see, this is a very interesting case. If it's plus or minus, and if I take plus, okay, 16 minus 12 is 4, so 4 plus 2, 6 by 6, it will be again R naught. That means this R is the same as the previous, that it didn't move. And we told that, right? Because there is no radial velocity. So the orbit should not get any bigger or smaller. That is one case. And if I take the negative sign, okay, for the minimum, I should take the negative sign, which is 4 minus 2 by 6 R naught, which is R naught by 3. Okay, this is the answer to this question. Okay, so this is an Olympiad question. I guess everyone understood the logic. Okay, it's a bit tricky. So after this, we are again having one more Olympiad question. Again, a bit more trickier than this also. Okay, so let's take a 5 minutes break. Okay. Okay, guys, welcome back, everyone. After this short break, let's take a look again at one of the Olympiad Chinese Olympiad problem. We have been given that every black tile of an insulating chessboard. Okay, this whole is a chessboard. It's an insulating chessboard. Okay, and every black tile of the insulating chessboard of dimension L by L. Okay, of dimension. This is L and this is L. Okay. Every black tile, okay, sorry. Every black tile has dimension L by L. Is painted with the uniform surface charge density, sigma, while every white tile is entirely neutral. This black tile has surface charge density, sigma. Okay. All these black tiles have surface charge densities, sigma. All right. And these white tiles in between are neutral. And these white tiles in between are neutral. Okay. Determine the electric field at a point L by 2 above the center of the chessboard without any integration. Okay. Now, from this center point above, okay, that is out of the plane of paper, we have to determine the electric field. Okay. Now, had it been a complete, you know, uh, if the completely it would have been painted, then we knew that it would have been sigma over 2 epsilon naught, right? Uh, Sigma over 6 epsilon naught because it's not a infinite sheet, it's a finite sheet. Okay, for a finite sheet, if we apply boundary conditions and all, you get the electric field as sigma over 6 epsilon naught. Okay, but this is only half painted. Okay, uh, now what I do is I take this chessboard. Okay, I take a copy of this chessboard. Okay, and what do I do? I take a copy of this chessboard. Okay, and uh, I flip it. Okay, I take a copy of the chessboard and I flip it. Now, if I flip it by 90 degrees, you can see that previously whichever spots had been, white. Okay, just keep in mind this spot. Okay, this spot, and see what happens when I turn it 90 degrees. It turns into a black spot, right? So if I turn it 90 degrees, the electric field at that point at L by 2 above will, because the sheet is the same, it will again become 2E, right? 2E, and all these black and white mixture will make a complete even black plate, okay, which is sigma over 6 epsilon naught. So the electric field due to only the black halves is sigma over 12 epsilon naught, okay? Since the chessboard is symmetrical about both diagonals, the electric field at points directly above its center can only be normal to the plane of the chessboard. Okay. Now observe that if we rotate chessboard by 90 degrees and superpose with the original chessboard, we will obtain a square plate of edge length L that is completely covered by a uniform surface charge density sigma. That is, these white spots will also turn black. Okay. Now we have determined that the electric field of such a setup is sigma over 6 epsilon naught. Okay. The electric field at that point due to the chessboard is this half of this value because half are white, half are black, half are neutral, and half are charged. Okay. So it is half of this value, that is sigma over 12 epsilon. Okay, that's the answer. It's the formula, but it's just a you know a tricky question that how you flip it and you apply your brains a little bit. Okay, that's what Olympiads are all about, right? Okay, so next another question from the same Chinese Olympiad. Proves that the direction of the electric field at an arbitrary point P with a finite line charge with a uniform linear charge density lambda and set AB always bisects angle APB. We are saying I have some finite line charge over here, A, B, and at any arbitrary point P, okay, uh, I'll have a direction, okay, I'll have the direction of the electric field, okay, at that point P, okay. An arbitrary point P due to a finite line charge always bisects angle APB. By given this, okay, this is suppose charged, okay, with a charge density lambda, and this direction line, okay, this direction line, okay, we are being asked to prove that this direction line actually bisects this angle, okay. We are being asked to prove that the direction line bisects this angle APB, okay. Furthermore, show that the magnitude of the electric field at P is this, where h is the perpendicular distance, okay, this is h, and alpha is half of angle AP, it is this angle is alpha, okay, it's saying this, okay. So let's start it, that the magnitude of the electric field at P, let's take any uh, infinitesimal element between theta and d theta, okay, and okay, uh, I say that from the center point, okay, from here, okay, uh, this is h, okay, and if you join this point, okay, so yeah, so the dE or the electric field is infinitesimal element lambda upon 4 pi epsilon naught r square dx, okay, and This x is h tan theta. Okay. So dx is h x square theta d theta. Okay. It's just the normal derivation which you guys have been doing in your boards. Okay. So h six square theta d theta, which is lambda d theta over 4 pi epsilon naught h. Okay. That is, the magnitude of the electric field does not depend on the angular coordinate theta. That is the E. Okay. It does not depend with the theta, but it depends on d theta. That is the angular width of the segment, not the coordinate. Okay. D theta is the change of the width in the coordinate. Now, consider two infinitesimal line segments that subtend angle phi with the angle bisector OP. Okay. This is the angle bisector. And here I consider infinitesimal elements and possess equal angular width d phi. This is d phi and this is d phi. Okay. Now, the electric fields at P due to the right and left segments are dE1 and dE2. This is dE1 and this is dE2. Since the magnitude of these vectors are equal, there is no contribution to the electric field perpendicular to the angle bisector. Okay. Applying this argument to all pairs, the net electric field at P to the line just must bisect because this component will cancel out. This will only stay and this will always be along the angle bisector. Okay. So it always must bisect angle APB. To determine a magnitude, we this derivation you already have done, right? The electric field, we have a line charge. Yeah, and at a distance h, point P, the angle bisector alpha alpha. This everyone knows, right? As a standard result. This everyone knows as a standard result, right? So I'm not again going forward to prove it. I was just showing that this came up as a question in a Chinese Olympiad. Okay. So yeah, I guess this is okay. So we can move on. Okay. This question. This question is actually from the International Physics Olympiad. Okay. This is actually a question, a mixture of electricity and magnetism, both. Okay. This will take a considerable amount of time to first read and understand the question. Okay. I'll explain it in detail. Let's take a 5 minutes break before approaching this International Physics Olympiad question. Okay. Okay, guys, welcome back again to this International Physics Olympiad question. Okay, uh, let's just read the question first. Refer to figure 5.1. A thin disk of radius r is placed in the xy plane. Okay, this is the disk of radius r placed in the xy plane. Okay, such that its center is at the origin O. The region above the xy plane is filled with a uniform electric field with a magnitude E pointing in the negative z direction. Okay. Whereas the cylindrical, this entire area outside even this disk is filled with this electric field. Okay. But this magnetic field, which is present in the upward direction, is only present in this cylindrical area, just above this disk. Okay. The cylindrical region bounded by the xy plane below and the cylinder with the infinite length whose base is at the disk is filled with a uniform magnetic field B pointing in the plus Z direction. Okay. Just remember the magnetic field is only in this cylindrical region and electric field can be found even outside the region. Okay. The region out this is outside this cylinder has zero magnetic field. Now suppose we fire particles carrying charge q, mass m, and speed v from O in all directions. Okay. In all directions. I take a gun. Okay. And I fire particles of q, m, n with the speed v in all directions from O. Okay. That's the question is saying. Okay. Isotropically, that means the probability of being fired in a certain direction is the same regardless of the state direction. It's equal probability that this will go in any of the direction. Okay. It's isotropically fired. We ignore the effects of gravity and interactions between the charges. Okay. Now, suppose that all collisions of the charges with the disk are elastic and that 50% of the charges are constrained to remain within the cylindrical region. That means all these charges are getting fired. Okay. But what is happening is actually only 50% of the charges are remaining within the cylinder. Rest 50% are going out of this cylindrical region. Only 50% of the charges are staying in this cylinder. Okay. Then find the radius of the disk. Now, uh, I'll try to explain you this thing. Uh, let's say, okay, please understand the concept first. I fire some particle with the velocity v, okay, or speed b, okay, at an angle theta. Okay? This angle is theta. Okay. Now, I can break this into components. Okay, this b cos theta and b sin theta. V cos theta in the z plane and v sin theta in the xy plane. Okay. Now I take both components and analyze. And if I first view from top to the xy plane, I'll see something like this. Okay. If I see from the top in the xy plane, I'll see something like this. That this is my disk. Okay. This is the center of the disk. This is the center of the disk. And particle is coming out, the velocity v sine theta. Okay, along the xy plane. Now, this is the magnetic field. This is V. So, the force due to the magnetic field is actually Q into V cross B. Okay. Remember this because this is the electrostatics chapter. So, I am telling you this beforehand that the force on a moving charge in a magnetic field is Q into V cross B. Okay. Now, V cross B means this V cross B. If you cross this, okay, if you cross this, you'll find that this is getting 90-degree of perpendicular force and it is getting deflected towards this side. Okay. Or in other words, it's getting a perpendicular force and it's getting deflected towards this side. It will turn like this. At this point, as the force is 90 degree, it does no work upon it, so the velocity doesn't change. Kinetic energy doesn't change. When it's here, velocity is like this, but the magnetic field is still perpendicular to the plane, right? So V cross B is again perpendicular, so it will again experience perpendicular force. So basically, it will move around like a circle in a circular path in the xy plane. Okay, due to this V sine theta component. Okay, now for this charge to remain confined within this. Okay, do you understand? Now this charge to remain confined within this cylindrical region, what can be the maximum? This is undergoing circular motion, okay, due to the magnetic field. What could be the maximum radius of this circular path or the maximum diameter of this circular path so that it remains constrained in this you know, cylindrical region? Of course, that circular path has to be something like this. Okay. It has to be something like this. Okay. This is R, which is being asked to us in the question. Okay. And the circular path for this charge has to be like this. It should just touch the cylinder and again go back. Because once it gets out, there is no magnetic field here. Okay. So it will just go away. It won't make a turn back. Okay. So this is the maximum diameter. Okay. If I say this, the radius of the path of the charge could be r by 2. Okay. And uh, the at this point, it will be moving like this. Okay. It's a uniform circular motion with speed v sine theta doesn't change because the magnetic field is acting perpendicularly. Okay. So this is mv sine theta square upon r by 2. Okay. And the magnetic field, okay, the magnetic field is acting Q into V cross B. And for staying in circular motion, these two have to be equal, right? These two have to be equal. So we will say that U U V P sin theta equals mv square tan square theta on by 2. So v sin theta cancel. From here you get R as 2 mv sin theta upon b. But the sin theta is not given to us in the question, so we need to get rid of it. Now, think there is one hint given to us in the question that 50% of the charges are constrained to be inside the cylinder. Now, these charges are released isotropically in an isotropic manner. Okay, so these charges are being released like this. If 50% of the charges are going away out of the cylinder and 50% are staying, that means this this angle is 90 degrees. Okay, all the electrons that are released at 45 degree is the critical point because all are released isotropically, all are similar. So this 45-degree angle, this V shape is the critical point. Inside of this V shape, all the electrons will stay in this cylinder due to the magnetic field. And all the other ones will jump out of the cylinder and go up. Okay. So this sine theta has to be here 45 degrees, half. Okay, because this is 90, this is 0 degree. In this total range, the particles are coming. So half of that will be the average value, which is 45 degrees. Okay. So R sine 45 is 1 over root 2. Okay. R would be root 2 mv upon qb. Okay. So this is the answer to the first question. Root 2 mv over qb. Okay. Now the second question. We now introduce a model of non-elastic collisions. Till now the collisions were elastic. Now we introduce a non-elastic collision. Okay. And suppose that when a charge collides with the disk, the direction of the purpose it went now this component, this V cos theta component, it will go up and the electric field is continuously working downwards. It's just like the Earth's gravity only in this case. It will go up and it will come down and again strike back the disk. Okay. So the perpendicular component of the velocity is reversed. When it comes back and strikes, the direction is reversed. Again, it becomes towards above. While that of the parallel component is unperturbed. That is, when it comes and strikes, the parallel component stays the same. The perpendicular component just reverses. Suppose further that the magnitude are reduced by the same proportion so that the kinetic energy of the charge is reduced by 10%. Okay. Now consider the projection of the charge's location on the xy plane. This charge is moving in a circular path like this, as well as moving in the z-axis. Okay. So if you see as a whole, it will be moving like this, somewhat like this. Okay. So if I consider a projection of this, that will be a circle in the xy plane, right? Consider the projection of the charge's location in the xy plane. Find the length of the path traveled by the projection during the period between the ejection of the charge and its first collision with the disk. When tough, it came down and it struck the disk once. How much length the projection has covered? That is, how much distance this circle has moved. Okay? How much distance the particle has moved in the circle in the circle. It's indirectly asking this question. Now, we've been given, but after we don't need to actually consider because we just have to find temporal ejection and the first collision. Okay, this question has actually had a second part. The first part, second part is actually a bit tough, so that's why I entered. It's not suitable for electrostatics discussion. Okay, that's why. Okay, now this it's going above v cos theta. Again, returning back and striking the disk. Okay, so if I put S is ut plus half at square, okay, it strikes back, so S is 0, okay. U is v cos theta, T, A is QE over M square, right? So T would be 2mv cos theta over QE. In this much amount of time, it will go up and come down and strike back the disk. Okay. And within this much amount of time, we are asked at how much distance the projection is covered, that this circle has covered. Okay. For that, we need to first find the time period of the circular orbit, right? Now, we saw that QVB sin theta is mv square sin square theta upon r. Mv square, okay, upon r. So this v sin theta is cancelling out. Okay. So the radius of the path is v sin theta over qb. Okay. And the time period is 2 pi r upon v sin theta, that is the velocity, the speed with which it is revolving. That is 2 pi over v sin theta into v sin theta upon qb. Okay. So you will get 2 pi m upon qb. This you always remember as a result that the time period of the revolution of the particle in a uniform magnetic field is always a constant. Okay. 2 pi m, q and v is always a constant quantity. It doesn't depend on the angle, the speed with which the particle is projected into the magnetic field. Okay. It's always a constant, that is 2 pi m upon qb. Okay. This you remember as a result. Now, in this much time, okay, in 2 pi m upon qb amount of time, it covered a distance of 2 pi r. Okay. We need to find how much distance it covered in this much amount of time. So in 2 mv, 2 mv cos theta over qe amount of time will have covered qbr over m into qe, sorry, into 2 mv cos theta over qe, okay, which is equals to b over m 2 mv cos theta into r. What is r? Mv sin theta by qb. Mv sin theta by qb. So this b to b cancels, m to m cancel, okay, which is mb squared 2 sin theta cos theta is sin 2 theta upon q e. So this is the answer that this much distance the particle will have, the projection of the particle will have covered. Okay. So two, no, no, and this was sine 2 theta upon QE, right? Upon QE. I guess it's pretty easy, obvious now the answer. Question is easy, but yeah, you just need to visualize things like this. Okay. This is the International Physics Olympiad question. Okay. Simple, but visualization matters more. Okay. Great. So let's move on to the next question for today. Okay. This question is from the National Standard Examination in Physics. Okay. It's a qualifier stage for the International Physics Olympiad from India. Okay. If you want to represent India in the International Physics Olympiad, then you need to start with NSCP, then IOQP, Indian National Qualifier for Physics. Then you need to give Indian National Physics Olympiad, INPHO. After that, you'll be selected as an Indian team to represent in the International Physics Olympiad. Okay, so this is the status. So, anyways, this question is from the National Standard Examination in Physics. Okay, uh, a long straight wire carries a charge with a linear density lambda. A particle of mass m and charge q is released from rest at a distance r from the wire. The speed of the particle as it curves crosses a point at a distance 2r from the wire is. Here being said, we have a long straight wire with a linear density lambda. Okay, okay, it's a linear density lambda. Mass m charge q released from rest at a distance r from the wire. At a distance r from the wire, particle of charge q mass m uh, is released, and at a distance 2r, when it reaches a distance of 2r, what would be its speed? That's the question, right? Okay. Now, electric field is, everyone knows, is the conservative force. So, the change in kinetic energy is the negative change of potential energy. Okay. So, we need to find the U initial minus U final. Okay. So, the electric field at that distance is lambda over 2 pi epsilon naught r. So minus bu is lambda over 2 pi epsilon naught r dr. So negative of the delta u is actually lambda over 2 pi epsilon naught ln r, where is from r to 2r, right? Lambda over 2 pi epsilon naught ln 2. And this negative change is the change in the kinetic energy, which is half mv square. Lambda ln 2 over 2 pi epsilon naught. This 2 cancels. So this V would be lambda ln 2 over m pi m epsilon naught square root. Okay. lambda log 2 over pi m epsilon square root. Okay. So I guess this everyone understood. So pretty easy question, right? Again, the conservation of energy wala concept. Okay. So I guess everyone is clear with this. Okay. So I guess we should now move with the next question, right? Okay. Yeah. So these two questions. Okay, let's first start with this question. This is a pretty easy question. You can do it very easily. So a particle of charge minus qm moves with a circle of radius r around an infinitely long charge of linear charge density plus lambda. The time period will be okay. So it's pretty easy, right? That is uh, mv square over r is lambda over 2 pi epsilon naught r. Okay. mv square upon r is lambda over 2 pi epsilon naught r to q. Okay. R to R is cancelled. Okay. So you get V as this. Okay. This you get as V. And the time period is 2 pi R by V, right? Okay. So what should be the time period? Uh, Pi R and the brackets asking in terms of A again. So M by 2K lambda Q. If you square it, uh, K lambda Q. No, let us square it. It's option A. Okay. 2 pi R over into square root of M over 2 K lambda Q, right? Okay. This question is easy. Done. All right. This is a pretty fairly common question. I actually saw in many books and test papers. That's why I included it here. Okay. Now, now we have over here this question. Okay. This is actually pretty simple one actually. Uh, it's saying that charge is distributed within a sphere of radius r with a volume charge density. This much is given in the sphere where A and A are constants. If Q is the total charge, then the radius R is. Okay. So easy, right? It's Q is equals to integral of rho dV. Okay. That is upon square e raised to power minus 2r over a after 4 pi square dr. Okay, solve this. You get 4 pi a minus a by 2 e raised to power minus 2r a minus 1. So you get it as 2 pi a minus 2 pi a e raised to power minus 2r over a. So that implies 2r over a is one of this. So you find r as a by 2 log 1 over q over pi. So this option, second one is the correct answer. Right? Just normal integration only, nothing much over here. Okay. Next question, also a similar like we have done with the differential charge distribution. Okay. It's like again the sphere is itself divided into two spheres. Okay. This sphere itself divided into two spheres. And this was smaller, it was capital R. Okay. The electric field at an internal point. Okay, so here the electric field we can apply Gauss law as we have done there also, okay. Which is surface integral E dot ds is 2 4 pi square is q enclosed by epsilon naught, right? What is the q enclosed within that area? Which is rho naught into 1 minus r over r. Okay, so dv. What is dv? 4 pi square dr, right? So this is 4 pi r square dr. So E into 4 pi r square is 1 over epsilon naught integral 0 to r rho naught 1 minus r over r 4 pi square dr. So from here you get the electric field at the internal point to be rho epsilon naught into r upon 3 minus r square upon 4r. Okay, this is the answer you get, which is option number B again. Right? This question is also clear. Okay. So we are left with these two very conceptual, very calculative questions.
if you see the answer, you will actually get amazed how long and large answers they are. Actually, very good and conceptual, these two questions. Okay, start with this question. Okay, then we have this question, then we'll move on to the PYQs. Okay, at the very end, I'll come back to the star questions, right? Let's just solve the star mark questions over here. Okay? And this Griffith's question is actually okay. So we'll take another break here. We'll take another break here and we'll start with this question. Okay.
Hello, guys. So, welcome back after this break to discuss this question. This is actually a great question. Uh, it's a very, very conceptual one. Okay. So, let's approach it. Two concentric rings placed in a gravity free region, okay, in YZ plane, one of radius r, okay, carries a charge plus q, and a 4r carries a charge of minus q. Find the minimum velocity. We did the same type of question earlier also, right? There, from a distance of 3r, particle was released, right? Find the minimum velocity with which point charge or mass m minus q must be projected on distance of 3r from the center of the ring so that it will reach to the center of the rings. Okay, so
Find minimum velocity with which a point charge should be projected from a point at a distance 3r from the center of the ring so that it will reach to the center of the rings. Okay. So first, let's draw the diagrams. Okay. You did this kind of question, right? This one. Did this kind of question, right? Yeah. So yeah. So it's like this. Okay. Run these two uh, concentric rings. Okay. Of Q minus 8Q. This is the center. Okay. And this is the radius for the inner ring. Okay. So this is the radius for the inner ring, and this is the radius for the outer ring, right? Okay. So yeah, all this is fine. Yeah, all this is fine. Yeah. And we are at a distance 3 here, we have a charge of minus q, right? So at a distance of 3 here, we have a charge of minus qm to be projected at a minimum speed so that it reaches here. Okay. Now the thing is, if you notice that at a distance 3r, the charge minus q will have, at a distance 3r, the charge minus q will have repulsive force from this ring. Okay, this minus 8q ring. Okay, but on points close to the center, it will have an attraction force due to this one. This ring dominates now, then this one when it's actually closer. Okay, so one should always be careful while applying the energy conservation equation in these type of problems. Okay, first we have to find out a point where the electric field is zero. Okay, because beyond that, charge will have attraction force. That point is the balance force between this and this, and inner to that, this will be more dominant and will be an attractive force. Okay, and if it reaches that equals 0 point itself, then beyond that it can go. It will itself reach the center of the rings because of the attraction force. Okay, so we basically need to apply the conservation law till that point where the E turns out to be 0. Okay, now the electric field would be at any point on the axis. Okay, would be K due to the inner ring first. Okay, due to the inner ring first, then the outer ring, right? The inner ring first, the outer ring, and we need to find a point of equivalence where both of them are 0. So if you solve this equation, we'll find that at x equals 2r, okay, at x equals 2r, the electric field is 0. Okay. So we have to give this charge enough kinetic energy so that it could reach till this point. Okay, because beyond this point, the force will be attractive, the electric field will be attractive, and it will itself get pulled to the center. Okay. Now we can apply potential energy equation between these 2 points, that is 3r and 2r. Okay, so potential at A. Okay, so I'm rubbing this. Okay, we found x equals 2r. Okay, so potential at A is K Q over 9r square plus r square by 2 minus 8q over 9r square plus 16r square power 1 by 2, just minus qk over r 16 minus root 10 by 10. Okay. Potential at point B, KQ 4r square plus r square by 2 minus K8Q over 4r square plus 16r square over 1 by 2, which is minus KQ over r 3 upon root 5. Now half mv square is KQQ upon r 3 upon root 5 minus 16 minus root 10 upon root 10. Okay. So from here you get the V minimum as 2 over m. Okay. 2 over m into 4 pi epsilon naught KQ upon r into 6 root 5 plus root 10 minus 16 upon 10 whole square. Okay. So this is going to be the answer. Okay. So easy one, you just need to know this point first. This is the concept over here. Till this point only you need to apply the conservation law, not till this point. Okay. Rest all is just a calculation. Okay. I guess it's done. So let's move on to the next question for today, which is this. This is another great question. It's saying a point charge Q is fixed at the center of an isolated disk of mass m(r). Disk is resting on a rough horizontal plane. Another charge minus Q vertically above the center of the disk at the height h. If the disk is displaced slightly in the horizontal direction, okay, at the period of oscillation, friction is sufficient to prevent slipping. Okay, this disk will roll back and forth like this. Okay, so if I now say that this minus Q is here, okay, and This Q is here, and it has been displaced, okay, because initially it was here, okay. So this is X, okay. This is H, and this will be the electrostatic force of attraction, okay. And these are the components, okay, of the attraction, okay. Now, and this distance is R, let's say. So this electrostatic force is K Q1 Q2 upon R square, and from Pythagoras theorem this follows R square is X square plus H square. Now the restoring torque, see, this is here, it's touching the ground, so about this point it will undergo like this, simple harmonic motion like this to this, okay, about this point, okay. So restoring torque about the contact point, okay. Restoring torque about the contact point is this component f sin theta into this distance, which is r, right? Okay, is equals to minus this, okay, into x over this. And this is a very small displacement, so after, so look at this, okay. So the restoring torque, okay, the restoring torque is now this, okay, and this x equals to h theta, okay, in radians. So this would be equal to this expression, which is directly proportional to minus theta. So this is an SHM, where omega square is equals to this value, okay. So or you can say that this torque is I alpha, right? So alpha is is QQR over 4 pi epsilon naught h square theta into divided by I, right? Okay, it is the one definition. Okay, so time period is 2 pi under root mod theta upon alpha. Everyone knows that. So from here, the 12 time period comes out to be 2 pi h under root 6 pi epsilon naught mr upon q. So this is the answer to this question. Okay. 2 pi h under root 6 pi epsilon naught mr upon q. Okay. So I guess these questions are clear to you. Okay. So yeah, then we could come over to this question. Now this question, there is a figure which shows two large cylindrical shells having uniform linear charge densities plus lambda minus lambda. The radius of the inner cylinder is A and that of the outer cylinder is B. A charged particle of mass m, charge q, revolves in a circle of r. Then its speed v is. Now this we can consider as the Gaussian surface or the Gauss law. So the surface integral, okay, is q enclosed by epsilon naught. Okay, so E into 2 pi RL. This much charge is enclosed by epsilon naught. So your electric field is lambda upon 2 pi epsilon naught r. This you know, due to an infinite long charge. So this QE is equals to mv square upon r. Okay. So yeah. So mv square upon r, that equals q lambda over 2 pi epsilon naught into r. Okay. So from that you get Vs square root of q lambda over 2 pi epsilon naught m. The first option is the correct answer. Okay. Yes, this one is easy. Everyone gets it. All right. So I guess we have solved all the questions. Okay, which are of JEE level, and we did this uh, physics Olympiad question. Okay, then this these all Olympiad questions also we did. I hope these questions put a confidence in you. These questions will do at the end. Okay, these are not for JEE, these are just for enhancing your understanding. Okay, so yeah, so all other JEE questions we have done. So I guess it's finally time to move on to the PYQs, or the previous year questions part. First of all, okay, the JEE archives or the previous year questions. Okay, this is again a very good question. We'll do it. First, uh, let's take a 10 minutes break before starting with the PYQs. Okay. This is again a very good question. We'll do it. to master. Hello guys. So we just had the only the PYQs were left and it is already late. That's why I thought we could take the PYQs over in the next discussion. Okay. Thank you everyone for a patient hearing.